Hey, this is Eli Peter, and today we're going over my final exam, the full, complete Turing code, or Turing Style Programming Language, ASA. Okay, so the detailed description of the feature that I chose to hint was the whole deal. I guess, yeah, I chose to do the conditional operators, some more than what was actually listed in there, if expressions, else expressions, else if, while loops, function calls, function definitions, the whole shebang. I think I'll just start off with maybe I guess I don't know what the best way to start is. Probably just the grammar, because it says here detailed description of feature you chose to implement, but I feel like that will come as we look at everything else. So first off, let's go on the grammar. So this, obviously we have the program grammar, which is the entry point to the whole program, and then we have a grammar to our functions, right? So, oh yeah, and a program can either be a function defined, a statement, or a comment. Although comments are actually removed, I made that change in my lecture, so technically you can just ignore that. Let's go on function defined. Function defined has to be a function fn followed by an identifier, which is just the name of the function, followed by its arguments, followed by either statements or comments. Okay, wait, sorry, my AirPod just died. Followed by statements or comments. Arguments can be the arguments are just a list of arguments separated by a comma. An argument is an identifier, and it can optionally have a default value, which is identified by an equal sign and then an expression. So, for example, you could have fn greet, name, and then equals, Eli. You know what I mean? As Eli would be the default value there when you call it functions. So you don't have to call it with any identifiers, with any arguments. Let's go over next is statements. Statements are pretty important because it's just the backbone of everything, as you can see. Statement can either be an assignment, a variable defined, an assignment, a function return, function call, break statement, continue statement, if expression, and while loop. Yeah. And I guess, because it would be, I don't know. I'll just keep going in the grammar, then we'll explain everything later. So next, we have variable defined, which is just either defined as let, and then the identifier, then equals an expression. We have assignment, which is the L value, and then equals expression. And then where L value is pretty important here. Yeah. So L value can be, we'll go over that later. Yeah, so assignment is L value equals expression, and assignments are useful for if you have let's say, so this is a variable defined, let x equals 5, right? And then you want to update it, so you do x equals x plus 1. That would be an example of an assignment. And the reason we have assignments with L values instead of just obviously an identifier is because we want stuff like this. So obviously you have your tape, right? I'm glad that GitHub knew what I was doing. And then we have tape at position 0 equals 1. This right here, if you go into L value, right, it can either be a property access or an index access. And a property access can be an identifier and then dot something. So this, technically you could expand my code even more to be let's say you had an object type, you know what I mean? Let's say you had type just a bland object, right? And it has, or a point, you have two variables assigned to that, x and y. This would allow you to do, x dot, or point dot x equals, you know what I mean? That is this, and that's not implemented, but that is this property access. And then there's also index access, which is just this and then an expression. So identifier and then an expression. Or L value could also just be an identifier, because obviously we don't want to just force, you know what I mean? Like you can also just have x equals. The next thing is function return, which is just return followed by either a function call, an expression, or an identifier. It's pretty basic. Function call is identifier surrounded by optional call arguments, or parentheses, and then optional call arguments, and then parentheses. Call arguments are like before with arguments. They're an expression followed by, like if there's more than one, followed by a comma and then more expressions. Break statement, continue statement, these I had to implement a little weird, that's why they're in the grammar, because they're actual nodes. That's the best way I found for this sort of control statement style stuff. So break statement equals break, and continue statement equals continue, which I guess should be, it is technically a statement, but it is in the control structure, I feel like. So maybe that doesn't matter. So if expression, so this is starts with an if, obviously, and then parentheses, which are optional. You can either have parentheses or you don't have to have parentheses, but you can't do a comma. You can't have one parentheses and forget the other one. That will result in an error. So it checks for if, and it checks for an expression, which it evaluates. And if it's true, then it looks for a statement or a comment under the brackets. We also have optional else if, right? And then another expression, so you can have as many of these else ifs as you want. And then you have your final else. We also have while loops. So while some expression, which again is optional on the parentheses. All of these with the else if as well is also optional with parentheses. I just know in the README it showed it without parentheses, but originally I had it implemented with, so I just kept them both. So while expression, statement, or comment. So now we go into expressions, and expressions work kind of like there's a priority queue which ensures that each one gets implemented at the right time. Like I implemented logical ands and logical ors, which, you know, obviously these have different priorities than equals equals. Like let's say you have like if x equals 0, example right here, or y equals 0. You won't want to do if x equals 0, or like, so this would obviously run, and then so this is whatever, let's just say this is true. So true or y, like that, you know what I mean? Like we don't have a boolean, like that's, y isn't a boolean, y is obviously a num, and that's what's happening before. So what I redid is I redid the way the parser does is it first checks, so expression links back to logical or, and logical or links back to, checks if there's a logical and first, and then it checks if there's a logical or. Logical and checks if there's an equality first before checking for a logical and. And obviously what I mean by that is it checks one side, checks if there's the logical or, like checks first there's a logical and on the first side, right? And then once it's parsed through this whole thing, then it checks and sees if there's a logical or, and then if there is, then it checks the other side first for a logical and, so then it parses the other side. Logical and checks for equality. Equality checks for comparison. Comparison checks for addition. Addition checks for multiplication, which also includes modulus. I added that as well. Modulus checks for multiplication. Multiplication checks for exponentiation. Exponentiation checks for unaries, which can also be not. I added not as well. So whatever, like, you know, not true equals false, stuff like that. Yeah, and then unary checks for postfix. Postfix can either be a primary or a primary with a dot identifier. So what this is basically, so primary is a number, identifier, a boolean, a string, array literal, or an expression surrounded by parentheses, right? And so what we want to do is we want to to, like, this might be, like, this might be an array, right? And if this is an array, maybe we want to have a dot length. We have a dot length after it, or we have some expression like, what if we have, like, take dot length is greater than or equal to 5. You know what I mean? So we're checking array first, and then we're checking if it's a postfix, and then we're checking if it's a primary and it has an identifier or an expression attached to it, or a function call, which would be obviously for future implementation, but that'd be like, yeah, that's way down the road. Yeah, but that's just for like if you have objects. Primary, yeah, it's either number, identifier, boolean, string, array, literal expression, L value, we already went over these. These are identifiers, or property access, which is identifier with a dot, or index access, which is identifier with an expression. Literal number is just a digit. Boolean true false. String is quotes, and actually it's anything. It's not just alphanumeric, so this is wrong. So obviously anything is allowed there. Array literal is brackets surrounding an expression, and then after that you have a comma surrounding any future ones you want to add to the array. Identifiers are either either one letter, or they're alphanumeric, which is multiple. Comments are 2 backslashes, and then alpha is just ABCD, all through lowercase and underscore. Digit is 0 through 9. Alphanumeric is alpha or digit. Yeah. And any valid characters except new line. Yeah. White space is deleted as well, so let me just push this. Sorry, I don't want to re-record. It's already 11:24. Okay, let's go. I did make some changes to the actual Lexer itself. Let's just go in here. We can look at these. So the changes I made were pretty basic. I originally was going to do an else if thing, because I had if and else, but then I realized I could just separate that into an else and then an if, like 2 separate ones. Tokens. I added a break continue. I did right bracket, left bracket. I didn't actually have not equal, so I added that. I added the logical and, logical or. I added the not. I added the modulus, and I added the dot here. I also updated the string by adding the string literal to make associates work. So all this is just the same as before, except for boom, you get to here. So when it originally opens up, when it gets the first character of that list, so while for list at length, it checks if it's a backslash, and if it is, it checks if the next one after that is another backslash, and if we're not going for list at length, we're being safe here, and if so, then it just eats all those characters until you get to a new line, and then you consume the new character and move on to the next line. This just ensures we don't even process it as like a comment block, because it was still causing some errors, so we just delete it entirely. The next one is the string literal. So we get the first quote, and then it will consume all the way until it gets the next quote. And we don't really check, right? Like we don't throw any errors in our Lexer right now, but one issue is that someone could have a quote and then not, you know what I mean? Like they go to the end of the file and there's still not an end quote, which should be an error, but right now we just parse that as a complete string literal. maybe not the best, but it does do the job. Yeah, I mean, all these are pretty basic, just checks for logical and logical or, either that or it's an other token. And so checks if there's two of them. These are pretty, we've been over these before. These are single characters, so they're pretty basic as well. And then right here we check for the break token by checking as BREAK in whatever sequence, and also if there's room left, and then continue, it's the same thing. Yeah. So lecture very basic. Parser is where you get a little more complicated. So we obviously have some new nodes. We have I think these were here previously from Horde 5. I don't know, we have a lot of new nodes. I know for a fact that these right here are new. Array literal, index assets, property access, and method call, along with break and continue. I think null has always been there. Yeah, method call just has the name of the method it's calling, and then the children, the first children, we can look at later, but the first children is the identifier. Like method call is made for stuff like tape.push, you know what I mean? So it would store .push as the name, or like not .push, sorry, push is the name. It would store tape as the first child, then it would store all the arguments as further children. So like obviously in the future, actually right now we have insert, right? You should insert like any position on that tape, which is implemented. So obviously this will be the first child, this will be the second child, this will be the third child. Property access, it's very simple. Index access, very simple. We can look at those later. I thought method calls a little more interesting. Yeah. I mean, I don't like none. Let's see. I just want to go into the. It'd be nice to have like my GitHub, whatever, like changes up that I did. Like if we could do a little comparison, that would be helpful. I feel like the parser is. Well, let's see if there's any. I guess we can just go over some of the stuff, like the function calls and stuff. You know what I mean? Like this is call arguments. Obviously, it checks for a separated list of expressions. Checks there's a comma and checks the expression after that. Function calls with the identifier first, and then after that it has the parentheses and then arguments after that, which are optional, and then parses that into a tuple. Yep. And so function call will actually be, I think it's the name is just the name of the function, and then the children are the arguments. And if there's no arguments, it's just an empty vector. Value. I don't even know if those used anymore. Oh, I guess so. I don't think this one actually is used. Because, yeah, that's talking about. Okay. Well, anyway. There obviously is some cleaning up that would need to be due if this was going to be any further than a test I did for a couple hours, but that was from homework 5. You have your expression here, which is just either if, logical or, boolean, function, addition, number, string, identifier, which obviously starts logical or is what we described before, that whole like path of equality here. So it checks the first one, then sees, hey, is there actually, two, I don't know what these are called, pipes, two pipes, like an OR statement, and then checks there's another logical AND after that. Just go through here. I guess if statement is a little complicated. Oh yeah, this is complicated because of the else if stuff. So right here, this is the optional. So it checks for if there is a left parentheses, then expression, then right parentheses, and then it checks for if there's just a expression. Probably a little inefficient, but such is life. Then checks left curly and then block right curly. So this is just for the basic if. After this is where we see if we have any more, if we have any if-else branches. So then it checks if there's an else, if there's an if, this optional parentheses, and then it checks for this block. And the block is just many statements. So, and then after all of this, it pushes to the children the condition first, and then the code it executes after the if else for each whatever if else thing. And then after that, we check if there is a optional else branch, and if so, then we just push that to the children. That is the final one. The while loop, way more basic. We check if there's a while token, either optional parentheses, expression, and then we check if there's a left curly and block, and then right curly. Break statement, we just check if there's a token add break, and then we put that as an actual node for break. Array literal, we check if there's a left bracket, and then we check for separated list of elements separated by a comma, and then expressions, so separated list of expressions. Postfix, this is primary, and then this dot and this identifier. This one got a little complicated because there's just a lot of issues with the fact that like you could have won with arguments, or you could have won without arguments. So, and then you also have ones with like expressions without expressions. So the way we do this is after it loops through, and for postfix we actually just do a loop here, and we match each sort of identifier or expression with the primary. After that, we check if there is any arguments, so left parentheses, comma, right parentheses, and if they do exist, so if they do exist, then right here, so this may be a method call thing, this optional thing, then it should have children 0 equals the object, children 1 is method identifier. So then we go through this, and it just generates them actually as a method call node instead of an index access, priority access, and then the children, obviously the first children is the object, and the children after that are the identifier. Sorry, yeah, all arguments, sorry. Error checking here, not implemented. Addition, basically this is implemented before, this is in homework 5. So this is all pretty basic. Yeah, primary is just the basic thing. It checks for if there's a parentheses around expression first, or function call, number, identifier, boolean, array, little string. Statement, we check for all these with the semicolons after them, and we check for if expression and while loop. Yeah. Spent a lot of time commenting this. this is pretty basic. Function return is pretty basic. There's some cool stuff going on in the interpreter. We'll look at it later. It actually has to do with the error code, because we return errors for break, continue, and function returns, which helps like guarantee that they get returned and broken out of whatever control they're in. Yeah. Block just mini statements. Okay, let's go into the interpreter. This is sorry, this is my interpreter. So we have a couple values. We have strings, we have arrays, which are just vectors, numbers, booleans, identifiers, or functions. Okay. This code is all from homework 5, which explained in homework 5. Okay, this is where we start going to do stuff. So we evaluate binary operations. This is sort of complicated because of just how many there are and how many different types. Like you have a plus here, right? And if you have a string and another string, then we just return, because we don't have two strings, we don't have any of the stuff in this equation. So we're doing this all natively in the back end. So then we check if it's a string and if it's a value, and we match it for all these different types of values. If it's, this might not be, the string might not be needed because it already checks it here, but that's just there for completion's sake. We check if it's a number, no, it has to be there, sorry, because our value is a value, and for the match to be exhaustive, we need to have string in there. So then we check number, so if it's a boolean, and we just do two strings. This is all back end two strings. Identifier, just ID, so that could maybe do memory address. Array, we just format the array. Yeah, and then function, we just do function, like literally just function. Yeah, and then now we check for, so this is if string is on like this side of it, and now we check for if string is on this side of it. And then we check for numbers, because obviously this is addition, so we add them together. And then the rest of the stuff we just can ignore. This is like if you have a number and an array, like, you know, like technically you could implement that as just a sum, but you can also do that natively in the code. And I'm not the biggest fan of stuff like that. I know that some of the stuff is in some higher level languages, but I'm not the fan of it. This is my language, so all these are just invalid types. And return a type mismatch. The rest of the stuff is matching left and right, and then the operator string. So this is just generic, any value. Because for equals and then not equals, we can just use Rust built-in equals and not equals. I guess technically for strings, this maybe, like I know with Java, I don't know if I don't know if this is, oh yeah, maybe this isn't the best thing to do if you have two strings, but I haven't seen any issues so far. I could obviously test that later, but I'm not going to do that right now because we're very close to how we need to submit this all by. So not equals, just generic again. And we check if these are numbers, because we have all of these, minus, multiplication, modulus, which obviously can't modulus by 0, divide, we can't divide by 0, exponent, greater than, equals, or greater than, less than, greater than, equals to, less than, equals to, or if we have two booleans, which is just the and symbol and then the or symbol, unary. This is where we do the not and the plus or minus, so you can have a negative number, or technically you could have a positive number. It's obviously default positive, so there's no need really. It just was already in there from before, I included before. And then we have not, so if it's a boolean, it does the opposite version of that, or if it's a number, Rust actually is interesting. Normally in like languages like C, if you do like not 1, it's 0. But it actually changes it to, I think, like -1, because it flips it does something different, but I thought that was interesting, and I wanted to keep that behavior in, so I just let it slide. So call function, this actually pushes to the stack. So if you go up here, the way this works is we create a vector hash map called like a stack for the actual interpreter itself, which just allows us to go through these like frames, as you can see here, like in like a stack sort of way. It kind of mocks, you know what I mean, like how an actual like operating system would work. Yeah, these are basic. These were explained before, but hash identifier, stuff like that, very basic. I didn't do any modification stuff like that. But let's go down to call function. Yep. So we want to create a new frame because we are calling a function. And then in that function, we are actually executing. So self to execute argument nodes 1. So what this is doing is this is returning whatever value you get from the argument. So self to x, so like, let's say you're calling a function with value with like an identifier x. This self to execute will get the actual value that x is attributed to. And if there's no value provided, we either use the default or we return an error. Yeah. And when we're finished, we pop from the stack, and we actually we have a couple things here. So this ASA error return signal is how we know we return from a function, because normally, like the return, if you're in a function, you called return, but let's say you had more code after that, it would just keep going. It wouldn't actually return. So we throw an error. So this picks up the error and sets it to the return value, whatever you get from this. Yeah, and then if you get any other error that's not the return signal error, then we pop on the stack and return that error instead of returning the return value. Execute, we just yeah, okay, so this is where you see this return signal. This, if you're in the actual execute function and you get a return error, it stops the function immediately. So you self to x for all the children, for every single node in the child. So we go through each thing on this parse tree. So we check the first thing parse tree, and then we go through all of its children. If we get a return signal, we immediately stop executing and we go back up. So we go through this is what I mean. This allows us to stop the whole thing. This by using these errors. And if it's not that, then we just return the actual error. And you see how we return OK value? See, we're not actually returning an error. It's just going up to the top value and returning that as returning the value. A lot of these, self-executing, it's like expression, we're executing as children because there's no expression node, it's just a wrapper number. We're evaluating the number, which is helper function, string, getting the string, bool, getting the bool value. Identifier, we are hashing identifier. Yeah, sorry, I don't know, this is not the best. I did most of this code at 4 a.m. for game last night, and I just finished the final. So, just trying to get through this video here to show off the cool things I've done. Oh. Yep. So unary expression, obviously we get the actual value of the expression the unary is tied to, and then we evaluate the unary. So like, let's say we have like not, 4 equals 5, whatever. We'd evaluate this first and this self-execute, and then we'd evaluate the unary, so we get the not. function define. Yeah, function define. We have arguments. We have our identifier, which we hash. And we have our default values as well. These are just for the exhaustive check on match, but they should never be reached, so they error out. Yep. Okay. So the cool thing is how about the children for if expression is, obviously first we have the condition, then we have the block, except for if it's an else statement, and then that doesn't have a condition, so it's a block. So actually we can check if it's odd, and then we know there's an else statement attached to it. But if not, we just go through each of these. So while children length, so we keep -1. And we just check, we execute the condition value, and we see if it returns true. And if it does, then we execute it at the index +1. And if not, we just return, we just skip and continue. And then we increment by 2. So what this does is this checks the condition, the value, without accidentally checking, without trying to execute the condition value is the else, block. You know what I mean? This gets this, this would execute 0, 1, and then maybe there's an else after that would be 2. Right, this is not going to execute that because we increment by 2. So the index this check will fail. And then we check, obviously, if it's odd, and if so, we execute the block. And if else, we just return untrue. While loop. This is where we have our errors for our break signal and our community signal. So we execute the children 1, which is just the block. And we actually have this in a loop, right? Because we just want to continue. And here we actually check if the condition value, because it's the first one, so first condition value, we execute the whatever condition value, so we execute that in this, we get its value, and we check that at the start of every loop, which allows us to short circuit. So we check if it's false, then we just break out of here with the true value, which is our default. And if it's true, then we execute it. If we get the break signal, which can happen at any point because it's an error, so it can break out at any point, there'll be a break. If it's the continuous signal, which can happen at any point, we continue, which just goes back and resets this loop. If it's an actual error, we throw that error and we return. And if it's just okay, we just loop again. Array literal, we just check all the children, we get their value, and we push that value to an array. Let's see. Okay, index access is pretty simple. Yeah. This is literally just we're checking for the index. So we obviously see if it's inbound, and if not, we return either as characters, if it's a string, or it's value. Property access, this is where we have our properties like dot length, so we have dot length here for for string and array, we match the object value. Method calls, we have our push, pop, insert, prepend. It's pretty basic. You can obviously have a delete one, but no need for that. Function call. This actually prints this, and then it uses. These are the 2 default values. So obviously we have our print statement with prints, then this returns, and we have our length, and then this returns, and then this goes and executes the self.call function, which is the one we described before. Yeah, I mean that's pretty simple. This is basically how it works. And then we can actually show you some of the cool tests we did. Main also. It's just a little error checking because we actually did the ASA thing. So you can see I've actually right here. Yeah, let's just go some of the interpreter tests. So we have, these are from before. These are our if-else statements from the whatever README. put them all in here. Yep, we have nested while loops. While loops with breaks. Yeah. Function returns constants. We have function adds. Function calculates. We have function called chain, so we call another function in a function. We function with default parameters. We have function requires arguments. So this calls with no arguments, this calls with arguments. Yeah, we have summing with different arrays. We have recursive. We have recursive Fibonacci. And if you see these, so it passes all 70 tests. Now here's this is the coolest test. This is the working Turing machine. So it has two inputs, the tape, which is the array. So I had to make I made the whole array, everything for this Turing machine. And then the position, which is just whatever number is the position. We get the state here. And while state's not equal to 2, which is our halting state, first off we need to expand the tape because it's an infinite tape. Obviously this is the whole reason I had to add the prepend, or the dot stuff after this, was so I could make it infinite. So if the position is less than 0, then we prepend 0, so we add a 0 to the start. We reset the position to 0 if it's greater than n, which is just n is the tape at length. Then we push, which pushes to the end of it, pushes 0. If state equals 1, this is just whatever basic Turing logic. But yeah, we also have to do tape equals tape to prepend, just the way that stuff works. But then yeah, we start with our initial tape of 1110, head position 0, we print it, we run it through, print it, and we return. And if we go here to our thing, we can actually call this, and boom, as you can see, it completes it. It does the correct steps of a Turing machine. It prints it out. It's Turing complete, and then returns 0. So yeah, that is my final. This is a very fun class. I don't know if there's anything more in my README you have to do over. Yep, let's see, I showed off all that. Yeah, thank you.